This is session C6, Particle in a Box Part 3, Superposition States. This will be the final session for Particle in a Box. We will explore superposition states for particle in a box in one dimension, both generally and specifically, and then watch simulations of their time dependence. We will use the normalized time-independent and time-dependent energy functions for particle in a box in one dimension that we've previously used. For a given system, problem, Hamiltonian, a superposition state is some or any static linear combination of two or more independent eigenfunctions of some given operator. We will use the energy eigenfunctions. The time-dependent superposition state wave function will be the sum across all eigenfunctions of the eigenfunction times a constant for that eigenfunction, and that constant can be and generally will be a complex number. So for example, for a particle in a box in one dimension, we have the ground state eigenfunction psi sub 1 and the first excited state eigenfunction psi sub 2. And if we take 2 times psi sub 1 plus psi sub 2, that is a superposition state wave function. It is not an eigenfunction. And we're interested in how does that behave? How is it different than an eigenfunction? First, we'll do normalization. Generally, we'll want the superposition wave function to be normalized. This puts a constraint on the coefficient c sub n. Let's determine this by taking the inner product. So the inner product of psi with psi needs to be 1 in order to be normalized. So that's psi of x and t, inner product with itself equals 1. And we can substitute for each one of those, we can substitute the series, the infinite series generally. So we can substitute for that in the bra and we can substitute for that in the ket. And when we do that, we need to use a different index in the bra and then the ket. So we'll use n in the bra and m in the ket. Now we can pull the summation signs outside the inner product. So sum over all n, sum over all m of these inner products. And we can pull the constants out, but we need to do that carefully. We can pull the c sub n out, but because it's in the bra, we have to pull it out as its complex conjugate, c sub n star. We could pull c sub m out, and because it's in the ket, we pull it out unconjugated. Now, we know that our energy eigenfunctions for particle in a box in one dimension are orthonormal, so we know something about this inner product. The inner product of psi sub n with psi sub m is the Kronecker delta, delta of n m, which is 1 when n equals m and 0 when n is not equal to m. If we were doing a problem where the energy eigenstates were degenerate, we would choose eigenfunctions that are orthonormal. So we end up with the sum over n of the sum over m of c sub n conjugate c sub m Kronecker delta of n and m equals 1. We can move the c sub n conjugate to the left of the sum over m. But when we take the sum over m of c sub m Kronecker delta of n m, this Kronecker delta is going to be 0 for every time that n is not equal to m, and it's going to be 1 when n equals m. So the only term of this infinite series that's going to survive is c sub n, where m equals n. So we get c sub n. So the sum over all n of c sub n conjugate c sub n, well, that is the magnitude of c sub n squared. So when the sum over n of magnitude of c sub n squared equals 1, then that wave function is normalized. That's the normalization condition. Now, the normalization constraint on c sub n is independent of time. If a superposition wave function is normalized at one time, it is normalized for all time. If we have a bound state wave function that is not or may not be normalized, we can normalize it. We can normalize it as follows. We replace each original c sub n with a new c sub n prime, which is the old c sub n divided by the square root of the sum over all n of the magnitude of c sub n squared. This is a multiplying by a constant, all terms by the same constant, and it's the constant that will make it normalized. So if we started out with 2 times psi sub 1 plus 1 times psi sub 2, that was not normalized because 2 squared plus 1 is 5, and it needs to be 1 to be normalized. So if we divide by square root of 5, then we get 2 over square root of 5 squared, that's 4/5, plus 1 over square root of 5 squared, that's 1/5, and that does equal 1, so this is normalized. Now, normalization is unique only up to an arbitrary phase factor. Any normalized wave function can be multiplied by e to the I alpha for any real alpha, and that resulting new wave function would also be normalized. This is a possible time to take a break. Superposition state. We want to learn how superposition states are different than energy eigenstates, but we want to do as little mathematical complexity as we can, so we're going to choose a pretty simple case. So for the rest of this lecture, we're going to use the following normalized superposition state wave function that combines the ground state and the first excited state for particle in a box in one dimension. No other eigenfunctions are included. So we're going to use the index S when we want to refer to this particular superposition state. So psi sub s of x and t will be alpha times psi sub 1 of x and t plus beta e to the I theta psi sub 2 of x and t, where psi sub 1 is the ground state energy eigenfunction, normalized. Psi sub 2 is the first excited state energy eigenfunction, normalized. We're going to take alpha to be real and beta to be real and require both of them to be positive. We don't have to do that, but we're going to do that. We're going to require alpha squared plus beta squared equal 1. And that will normalize psi sub s. Now, if it's not clear to you that this wave function is normalized, please verify it for yourself. Now we can substitute in psi sub 1 and psi sub 2, and we get this. So that's the wave function, the superposition state wave function that we're going to use for the rest of this lecture. Now let's look at time t equals 0. At time t equals 0, the exponents become 0, so we get e to the 0, we get 1, and the time dependence goes away. So we get psi sub s of x at time t equals 0 equals this. However, beware. you might write this as lowercase psi sub s of x, not t, but don't be confused. That might look like a time-independent wave function, but it is not a time-independent wave function for this particle in a box in one dimension, because this superposition state is not an energy eigenfunction. E sub 1 is not equal to E sub 2. There's no energy E for which psi sub s of x and t equals lowercase psi sub s of x times e to the minus I e t over h bar for all time. If you try to find such an energy, you won't be able to find one. And time independence is not separable for superposition states. So a lot of the simplification that we were able to do in previous lectures for energy eigenfunctions, we cannot do for superposition states, and we have to be careful. We must not try to apply formulas from lectures C4 and C5 that were applicable only for energy eigenfunctions, because the superposition state is not an energy eigenfunction. We must use the time-dependent wave function, psi of x and t, for calculations on the superposition state, as we will do in this lecture. If we were given some system and some wave function, psi of x at times t equals 0, that was valid for the Hamiltonian and the time-independent potential energy function at time t equals 0, there is a procedure for decomposing psi of x at time 0 as the sum of normalized time-independent energy eigenfunctions, psi sub n of x, and then a procedure for expressing psi of x and t as the sum of normalized time-dependent energy eigenfunctions, psi sub n of x and t, the time evolution. However, we will not do these in this lecture or this course. That is covered well in books and in the MIT courses, but we're only doing an introductory course. We're not going to do that. This is a possible time to take a break. Probability density. Let's calculate the probability density for the normalized superposition wave function psi sub s of x and t. We'll call this rho sub s of x and t, and it's psi sub s conjugate times psi sub s. Now, this will be the final lecture that has a lot of math about spatial problems. And as such, I want to give you an opportunity to challenge yourself to solve these problems without my help. So, if you've been following all the lectures so far, you should be able to calculate rho sub s, because we know what psi sub s is. So you could take the complex conjugate of it and multiply it by psi sub s and do the math. The math is in this case just algebra, no calculus. You can do that. You can get the answer. So I want to challenge some of you to go ahead and do that by yourself, and then scroll, go forward and find my answer and check yours. Now, if you're not ready to do that, if you want to go step by step, that's fine. I'm going to give you the steps. But what I'm going to do for this lecture is I'm going to stop explaining how I got from each one step to the next, so that you have the opportunity to challenge yourself to see if you know how I got from step to step. So there's going to be some dead air as I scroll through the solutions and not explain how I went from step to step. And then once we get the answer, I will explain the meaning of the answer and the takeaways from the answer. But there will be a little bit of dead air. Obviously, you can push forward to the answer if you don't want to see the math at all. So I'm slowly going to scroll from one formula to the next. And you can check each of these formulas for yourself and check that you understand the reasoning and how we got from step to step. Now for the remainder of this lecture, omega will be equal to E2 minus E1 over h bar. Those are the only two energies involved in our choice of which superposition state we want to look at. So here in green is the answer. Here is the probability density for that particular state, psi sub s. 2 over a times the quantity alpha squared, remember alpha is real, sine squared of k1x, plus beta squared, remember beta is real, sine squared k sub 2x plus 2 alpha beta sine k1x sine k2x cosine omega t minus theta. For x in the box, 0 to a, outside the box it is 0. This probability density for the superposition state psi sub s, it is real, as were the energy eigenfunctions probability densities. This probability density for the superposition state is time dependent, unlike the energy eigenfunctions probability densities, which were constant in time. See the cosine omega t minus theta term here. This probability density for the superposition state is periodic with period. Capital T is 2 pi over omega, or 2 pi h bar over E2 minus E1. Now if we integrate this probability density in space from 0 to a, we get 1 for all times. The particle is in the box for all time. This is a possible time to take a break. Let's take a concrete example. Let's take alpha equals 2 over square root of 5, beta equals 1 over square root of 5, and theta equals 0. So we get psi sub u, this concrete example. We could plug in alpha, beta, and theta, so we get rho sub u. And we're going to graph it. It's time dependent, so we're going to graph it for 5 particular times where omega t is 0, pi over 2, pi, 3 pi over 2, and 2 pi. So the bottom green curve here is omega t equals 0. So here to the left, we're outside the box. The probability density is 0. Then at 0, we are in the box. There is a probability density. And at a, we're greater than a, we're no longer in the box. Probability density is 0 outside the box. This probability density is a function of time. The lower green curve is omega t equals 0. And the probability density is bunched to the left half of the box. Now this green dot here, that is the expectation value of position at time t equals 0. We will calculate that later in today's lecture, but I want to show you the dots now, even though we don't have that formula yet. So the probability density is bunched to the left, diminished on the right half of the box. There happens to be no node for this particular superposition state. and the expectation value is not in the middle of the box at this time. Now, at the red curve, this lower red curve is for omega t equals pi over 2. And at that time, the expectation value is in the middle of the box. The probability density is symmetric around the middle of the box. The probability density has moved from the left side to being centered. Now the blue curve is omega t equals pi, and the probability density has shifted to the right side. The expectation value is on the right side. The blue curve looks exactly like the green curve, just flipped with respect to the center. And then as we continue in time, we move back from the right to the center to the left again. So probability sloshes from the left side to the center to the right to the center to the left. In this case, there are no nodes, no points within the box where there is zero probability density for the particle being located at that point, but that's only because of the particular case we chose. Typically, generally, superposition states would have nodes within the box. So don't be misled and think that there will never be nodes. It's just the case we chose. Now, let's graph the time-independent and time-dependent components separately. Outside the box, they're all zero, but here we are inside the box. The red curve is the time-independent portion of the probability density. Different scale than the previous graph. And then the green curve and the blue curve, which is the minus of the green curve, show the time-dependent portion. Notice how they agree as we get close to the walls, which means if you add the two, it doubles. But if you subtract red minus green or red plus blue, it gets to be very close to zero. Not exactly zero, but very close to zero. So the red, we alternately add the green curve to the red and then add nothing, and then add the blue curve to the red and then add nothing. That's how the time dependence works. This is a possible time to take a break. Probability current. Let's calculate the probability current for a normalized superposition wave function psi sub s. In one dimension, the probability current, J sub s, is h bar over m, imaginary part of the wave function conjugate times the partial derivative with respect to x of the wave function. Now, you could challenge yourself to do this math and see if your answer agrees with mine, or you can challenge yourself to see if you understand each step, and I'm going to not explain each step. I'll just scroll through them. I'm not sure why that scrolled off to the right there. So this is the answer. The current density is a constant, H alpha beta 2 over MA, times a time dependence, sine omega t minus theta, times an expression that is position dependent, K1 sine K2x cosine K1x minus K2 sine K1x cosine K2x, which we can't simplify further with trigonometric identities because K1 and K2 are different. That's the current density in the box. Outside the box, it's 0. So this probability current for the superposition state is real, as were the energy eigenfunctions probability currents. Those were 0. This is not 0, but it is real. This probability current for the superposition state is time dependent, unlike the energy eigenfunctions probability currents, which were constant and 0. This probability current for the superposition state is periodic, period t. If we integrate the probability current with respect to time over one period, we get 0 at every position. The probability density returns to its original curve. Now, the current density is proportional to sine omega t minus theta. Let's graph the probability current for two values of omega t minus theta. We'll graph it for pi over 2, which will be the red curve, positive probability current, and 3 pi over 2, the purple curve, negative probability current. If for omega t minus theta equal integer times pi, it's going to be 0. So for this particular superposition state, it's fairly simple. The probability current is either 0 at some time, or it's positive everywhere inside the box at that time, or it's negative everywhere inside the box at that time. This happens to just be a very simple superposition state. Easy to understand. So let's look at this red curve. At the time of the red curve, the current is highest at the center of the box. Probability density, current is positive, probability density is moving left to right, and the magnitude of the current is highest at the center of the box. Here toward the far left of the box, the current is not so high. Probability density is moving left to right, but the magnitude of the current is smaller here. This is a possible time to take a break. Probability current conservation equation. Let's verify the probability current conservation equation for this particular case, this particular superposition state wave function, its probability density, and its probability current. In order to verify it, we need to calculate the time derivative of the probability density and the spatial derivative of the probability current. Well, you already have both of these values, so if you know how to do these derivatives, you can then verify the equation. So I'm going to give the steps, but skip some of the work and not give you the play-by-play, and give you an opportunity to do the math for yourself if you so wish, or skip ahead to the answer. So after we do all the work, we do find that when we substitute the values back into this equation, we do get 0 at all positions and at all times, and the probability current conservation equation is satisfied. This is a possible time to take a break. Expectation values. We want to calculate the expectation values of certain observables. In this lecture, they're always going to be not explicitly dependent on time. For the normalized superposition wave function psi sub s for particle in a box in one dimension. So we can do some work keeping the observable O generic, and then that'll save us some work later when we plug in specific observables. So we'll start by keeping the observable O generic. So the expectation value of O is equal to the sandwich of O in state psi sub s, which is also identical to this integral. It's defined as this integral. Psi sub s conjugate, O operating on psi sub s, integral over all space. As a first step, let's write the sandwich of the two normalized time-independent energy eigenfunctions. So lowercase psi sub m O operating on lowercase psi sub n. That would be this integral, and that's big O sub m n is defined as that. This you may see this in books as called the mnth matrix element of operator O in this basis. Now, in the special case that the energy eigenfunctions are also eigenfunctions of operator O, which sometimes will be the case and sometimes won't be the case, but if it is the case, then O psi sub n equals little o sub n of psi sub n. And in that case, the sandwich of the matrix element, psi sub m O psi sub n, is going to be that eigenvalue, O sub n, times the Kronecker delta of m and n. So that's because the eigenfunctions are orthonormal. So in that case, if m were different than n, the sandwich would be 0, and when m equals n, the sandwich will be little o sub n. Now, additionally, it will also be true if we use the time-dependent capital psi's. So in this case, we could say that the matrix for operator O is diagonal in that basis because of the Kronecker deltas. Now, this is not a finite matrix. Don't be looking for the finite matrix here. It's an infinite matrix. We're not really going to deal with that, so we're just going to use the terminology. Now, it would be okay for the eigenvalues O sub n to be degenerate. They don't have to be non-degenerate. Everything we've just said, it would still be true even if they were degenerate. Now, if we replace generic operator O with the Hamiltonian H, and we use the normalized energy eigenfunctions, the matrix element of psi sub m H psi sub n is going to be energy E sub n delta mn. This is a possible time to take a break. Now, let's start calculating the expectation value of general observable O for the normalized superposition wave function psi sub s that we've previously defined for particle in a box in one dimension. So that expectation value is going to be this sandwich, psi sub s O psi sub s. And in a previous lecture, I gave some rules of how we could handle the bra and the cat in a sandwich. So we could substitute for psi sub s, and then we can use some of the sandwich rules, or the rules for bras and cats, and we're just doing algebra. Now, in this case, alpha and beta are real. Theta is real, so e to the I theta is complex. Psi sub 1 and psi sub 2 are complex. So we have to remember that, because when we pull something out of the bra to the left, we have to conjugate it. But remember, alpha and beta are already real. So I'm going to shut up and let you try to do the math if you wish. I'm sorry, the rendering here sometimes is a little funny and it won't keep the angle bracket with the term. I couldn't make it do that. Okay, so here's the answer for generic operator O with our specific psi sub s, turning it into its eigenfunctions, psi sub 1 and psi sub 2, that it is composed of. Now we can use this for specific operators. This is a possible time to take a break. Let's start with energy and the Hamiltonian operator. So instead of operator O, we're going to have operator H. Now we already know that the matrix element, the matrix elements with Hamiltonian H when the index is the same on the left and right, we get that energy eigenvalue. So we get alpha squared times E sub 1, beta squared E sub 2. But when the index on the left and the right are different eigenfunctions, the matrix element will be 0 and go away. So this is the expectation value of energy for our particular psi sub s. The expectation value of energy is real, as it must be, for an observable, a Hermitian operator. The expectation value of energy is independent of time, even though the probability density and the probability current are changing in time. The expectation value of energy is independent of the phase theta. If we make an energy measurement on the superposition state, psi sub s, we will either get energy eigenvalue E sub 1 or energy eigenvalue E sub 2. We will not get any other energy. You get one or the other. The probability of getting E sub 1 will be alpha squared. The probability of getting E sub 2 will be beta squared equals 1 minus E alpha squared. Now how do we know that? We get that from this expectation value. We get the expectation value of energy E is alpha squared times E1. So alpha squared is the probability of us getting E1 plus beta squared E2. Beta squared is the probability of getting E2. This system is not classical. When we measure it, we don't get a single, there's not a single result for every measurement of the system. We'll either get energy E1 or energy E2. They have different probabilities, but on any given time that we're taking a measurement, we don't know whether we'll get E1 or E2, and we could get either one. Yes, they have different probabilities, but each probability is non-zero. So we could get that energy. If we have 100,000 identical systems, each in state psi sub 2, and we measure the first one, we measure energy, maybe we'll get E sub 1. If we measure the second one, maybe we'll get E sub 1. If we measure the third one, maybe we get E sub 2. But we can't predict, other than probability, we can't predict whether we will get E1 or E2. The expectation value of energy E is generally not the arithmetic average of E1 and E2. It's weighted by the probabilities alpha squared and beta squared. There is one case in which you get the arithmetic average if alpha and beta are 1 over square root of 2, but in general the arithmetic average has nothing to do with measurements. The measurements depend on the probabilities. The probabilities depend on the coefficients alpha and beta, or C sub 1 and C sub 2, in the superposition state. Now, after making an energy measurement, the system will have collapsed to either energy eigenstate psi sub 1 or energy eigenstate psi sub 2, depending on which energy eigenvalue the measurement produced, and it will no longer be in superposition state psi sub s. So we can remeasure it, but we will get no further information about psi sub s because it's not in state psi sub s anymore. Now, the uncertainty in energy delta E is non-zero for the superposition state. It's not an energy eigenstate. We could calculate delta E, but we're not going to do that. This is a possible time to take a break. Now, the expectation value of energy, observable Hamiltonian, for the normalized general superposition wave function, psi, not psi sub s anymore, but the general one, psi, for particle in a box, you could calculate it and you would get that the expectation value of energy is the sum over all indices, which might be infinite number of them, of square of the magnitude of the coefficient C sub n times that energy eigenvalue E sub n. So the probability of getting E sub n in a measurement is going to be the square of the magnitude of C sub n, assuming the E sub n's are non-degenerate, which they are in particle in a box in one dimension. The expectation value of energy is real, as it must be. The expectation value of energy is independent of time. The expectation value of energy is independent of the relative phases of the coefficient C sub n. If we make an energy measurement on superposition state psi, we will get one of the energy eigenvalues whose coefficient is non-zero. The probability of getting E sub n is the square of the magnitude of C sub n if E sub n is non-degenerate, so there's only one term for it. System's not classical. After making an energy measurement, the system will have collapsed to the energy eigenstate psi sub n, corresponding to the energy eigenvalue E sub n, if it's non-degenerate, which particle in a box in one dimension is. It's no longer in superposition state psi. The uncertainty in energy is non-zero for the superposition state. It's not an energy eigenstate. This is a possible time to take a break. Expectation value of x. Let's calculate that for superposition wave function psi sub s. We could take our generic form for operator O and plug in operator x. And you can crank the math. You can use information we've obtained in the last lecture, C5. You can do integrals using Wolfram alpha, or we may have done the integral already in lecture C5. We know what K1 and K2 are. So here we have the answer, the expected value of x. The expected value of position for this superposition state, it varies in time, cosine omega t minus theta, oscillating around the middle of the box, a over 2. If we take the expected value of position and average it over one period of oscillation, the average expected value is a over 2, the middle of the box. If you substitute in numbers, the amplitude of the oscillation is at most 0.18 a. The expected value of position always remains within the box. Now let's graph the expected value of x horizontally as a function of time vertically. And to do that, we're going to choose particular values. Alpha is 2 over square root of 5 and beta is 1 over square root of 5. So here's the box, 0 to a. This is expected value of x. It starts out on the left side of the box, moves to the middle, to the right, to the middle, to the left, and repeats. This is a possible time to take a break. Let's calculate the expectation value of momentum for superposition wave function psi sub s. Again, we have the formula for a generic operator O. We substitute in operator P. And then it's just math. We know something from last lecture, C5. We have an integral. Maybe we did that in lecture C5. We certainly can do that with Wolfram alpha. We know what K sub m is, K sub n. And here we get the answer. 2h bar I over a, nm over m squared minus n squared, expression cosine m pi cosine n pi minus 1. This is all for m not equal n. This matrix element is imaginary because of this I, but it is sometimes 0. Some values of m and n will make this expression 0. Reversing m and n negates this value, so complex conjugates it. Reversing m and n here does not make a difference. Here does not make a difference, but in the denominator it negates it. Now we're interested in the case, the matrix element 1, 2 and the matrix element 2, 1. Here's the matrix element 1, 2. 2, 1 is the complex conjugate of it. And now we can plug back into the expectation value of P and simplify it, and here's the answer for the expectation value of P. We can simplify this. And here's the simplified answer. Alpha is real, beta is real, 16h bar over 3a is real. Sine of omega t minus theta is real, so the expectation value of momentum is real. It varies in time, oscillating around 0 momentum in this case. If we take the expected value of momentum and average it over one period of oscillation, the average expected value is 0. There is a maximum amplitude of the oscillation. We could graph the expected value of P versus time, and you can do that if you're interested, but I'm going to graph something a little different. Expected value of P is a function of time, and the expected value of X is a function of time. So we could graph the expected value of P versus the expected value of X, each being parametric functions of time. And we get this ellipse, where time is traveling clockwise in this case. So at this point here, the expected value of X is as far as on the left side as it's going to be. The expected value of momentum is momentarily 0, but then time moves on and the expected value of P becomes positive, which means we have motion left to right. The probability current is moving left to right. That continues until the expectation value of P has its maximum value when we've returned to the center of the box. Now the expected value of P starts to decline. It's still positive until we get as far to the right as we're going to get, and then we reverse ourselves. Now this phase plane graph looks like a classical oscillator, but we're graphing we're graphing the time-dependent expectation values of position and momentum here, not the instantaneous position and momentum, which are undefined for a quantum mechanical system. So beware, do not think of this as the trajectory of a particle, a classical particle. The quantum mechanical bound state does not have a trajectory. It does not have classical motion. It has probability density, probability current, and expectation values, which vary in time in this case. Now, all expectation values that we calculated in this lecture were real values because we always used observables, Hermitian operators. We could calculate the uncertainties in position and momentum for this superposition state, but we're going to skip those. This is a possible time to take a break. What we're going to do now is watch a simulation of particle in a box in one dimension from Falstat's website, falstat.com, mathphysics.html. I'm going to post this simulation in two places. It'll be here at the end of lecture C6, and it will also be C6b for people who skipped over 6 but might still be interested in seeing the simulation. You don't need to watch it twice, so it's identical in both locations. Here we are at falstat.com. We're going to click on Math and Physics Applets. He has applets for a number of math and physics cases: oscillations and waves, acoustics, signal processing, electricity and magnetism, electrodynamics, quantum mechanics, hydrogen atom applet. That's pretty interesting. We're not going to cover that. Molecular orbitals. Lots of interesting quantum mechanical stuff. We're going to look at one-dimensional quantum mechanics applet. Now, we can choose different problems: infinite well, finite well, harmonic oscillator, other things. We're going to look at infinite well for most of our time, and then at the end we will look at finite well. We have different portions to the screen. This upper portion is showing us different energy eigenvalues. It's hard to see down here because they're closely spaced, but you see that they get spaced out more as we go to higher values. I don't think I can expand this section to show us. Now, this second section here, I currently have it showing us the probability density. So that's this curve. And you see that the color is changing. That's the phase. Phase is getting mapped to colors. I'll change this a little later and show you different things. The red line here is showing the expected value of position. We're in the ground state right now. So the probability density is symmetric with respect to the center of the box, and there's no node, and the expected value of x is the center of the box. I'm going to make the box a little smaller so that you can see that it is 0 outside the box. Now this third pane here, the third pane here is momentum, but I can't expand this horizontally, so it's hard to see the momentum. This fourth pane here, this is called phasors. It's the amount of different eigenfunctions that are included in the wave function, the amount and phase. I'll explain this a little later. Now, we can view the wave function as probability or as the wave function, but the wave function is complex, so it has a real part, an imaginary part, it has a magnitude. If we want to look at the wave function, not the probability, well, let's do real and imaginary parts. The real and imaginary, we're in the ground state, the real and imaginary parts are changing in time. We know that because it's the time dependence is e to the minus I e sub 1 t over h bar, so the real and imaginary parts are changing. Let's see if I can show us, if I can get it. Okay. Now I've changed from the ground state to the first excited state. There is a node at the center of the box now. So we're seeing the first excited state wave function, real and imaginary parts. We're seeing the real and imaginary parts of the momentum here. We could look at higher energy eigenstates. I'm going to change the view so that we look at probability plus phase. Now, when we look at probability plus phase of an energy eigenfunction, here we're in the first excited state, the shape is not changing in time, but the colors representing the phases are changing in time for both position and momentum. Now what we're going to do is create a superposition state consisting of the ground state plus the first excited state. And when we do that, we see that the probability density, which is this pane here, the probability density is changing in time. It's sloshing from the left side of the box to the right side of the box to the left side of the box periodically. The expected value of position, the red line here, is changing sinusoidally in time. The momentum is changing also, but it's too clumped together on this display for us to see very well. We can speed this up some. Here's low mass. And for large mass, the energy levels became closer together. and the energy levels became smaller, the energy eigenvalues, and so the period became larger, so slower. I encourage you to play with this yourself. Now we're going to do something that the simulation allows us to do. We're going to measure the energy. We're in a superposition state consisting of the ground state plus the first excited state. When I click this, we will measure energy. When we do that, we collapsed to, in this case, the first excited state. Now, if we remeasure energy, we can remeasure energy all we want, and it's always going to, we're in an energy eigenfunction now, so measuring energy is not going to change anything. Let's see if I can go back. Back to a superposition state and tell it to measure energy again. This time, just randomly, we ended up in the ground state. Let's see if I can get us back there. Okay, we're back in the superposition state. Now I'm going to ask it to measure position. What do you think will happen? Boom! Look at all these phasors. When we measured position, we got a value of position. We don't know what it is, but we then got put into a state which is not an energy eigenstate at all. It's a combination of all of the energy eigenstates. It's a superposition state, but boy, it's not a simple superposition state. Look at how complicated the system is now. Let's go back to ground state. Okay, I encourage you to play with this, get a feel for superposition states and for energy eigenfunctions, a nice graphical feel that you can get to a limited extent with equations and graphing, but the simulation is really helpful. Now I'm going to do one other thing. I'm going to go to finite well. We didn't do the math for finite well, but I said earlier that for finite well, we can have probability density outside the well. So in this energy eigen, it's hard for me to show it because if I move the cursor, so if you look right below the cursor, you'll see that outside of the well, to the right of the well, there is non-zero probability density. It's an decaying exponential, but it's not zero. In the infinite well, it was zero. But for the finite well, there is non-zero probability density outside the well. Now let's reduce the well depth. Can't really see it very much anymore, but I broke the simulation. It turns out in one dimensions, no matter how small the well is, the depth of the well, there always is still a bound state. That need not be true in 2 dimensions and 3 dimensions, but in 1 dimension it is. Let's reduce the well width. Here we can definitely see that there is probability density outside the well for a finite well. Okay. If you want, you could play with harmonic oscillator. Or 2 wells. Or other cases. Okay, I encourage you to play with that and be aware of that for its other simulations as well. This is the end of our treatment of particle in a box in 1 dimension, both energy eigenfunctions and superposition states. We're done. Next lecture, C7, we're going to wrap up spatial issues by identifying issues that we're not going to cover in this introductory lecture series that you would get if you take the MIT course or you read a book. This is the end of lecture C6.